did we get through the articles that I posted yesterday,
Yes.
right? Okay, so we're gonna start off by just going through those real quick. That were up here, but they're not.
They're right there. They're right there,
Are-
I think. Look underneath that periodic table.
Oh, they're there. Okay. So, did we go through the notes as well? Did y'all fill up the notes as well? Because it might be easier to go through the notes. Did y'all fill the notes? You didn't get to fill in notes? Okay, so we'll start off with using what we learned in the articles to fill up these notes. And I think that might be a better use for the articles here today. Just so we can get to the point we all need to be able to class here. Okay. I'm going to turn on here. Make sure we're there. So, we did kind of go over John Dalton's theory, but go ahead and pull out those fill-in notes. We're going to quickly go through them, like I said, and then we'll move on to some new material. You probably need up to the second page. We'll be going all the way through nucleus. And that's what we're going to do with this
Are
one.
we supposed to like type on the document?
You can do that. If you have it printed out, you can print it out and write on it. It just depends on what's easier for you.
I don't think it lets you type on it, does it?
I just made a copy and turned that in.
Oh.
Gotcha. If it doesn't let you type, then I would suggest just like writing down the fill-ins, and then you can kind of go through later and fill in the notes from there. This is the wrong source. There we go. Right source here. So, let's start it off here. So, who could tell me what the smallest particle of an element that retains the property of that element is? Creed, immediately with your hand up. What you got? Atom, right? What we're talking about today. So this one, kind of the start of everything. So, let's move on to John Dalton's theory. So we kind of talked about the blanks here when we were talking about on Monday, but we're just going to kind of quickly refresh your memory, see if we remember this part. So, again, we have the first part, all elements are composed of tiny indivisible particles called atoms. Second part here, atoms of the same element are, so what was John Dalton's kind of misunderstanding on this one? What did he think all atoms of the same element were?
Indivisible, or identical.
They're identical, right? So he thought that every single element was identical. Good job, Keith there. So, and atoms of any one element are different from the atom of any other element. Number 3, atoms of different elements can combine with with one another in small what? To form compounds.
Whole number ratios.
Whole number ratios, right? Again, this is kind of defined as the law of definite composition, which we kind of discussed on Tuesday, right? And then 4, chemical reactions occur when atoms are separated, joined, or rearranged. However, atoms of one element are not changed to atoms of another element in ordinary chemical reactions. Now, going back into present day theory. Again, pretty easy to fill in here if y'all remember the stuff from Tuesday here. So, an element is composed of extremely small particles called what? Yeah, atoms, right? We just said that like a couple seconds ago for the first one. But yeah, sounds pretty good there. Atoms of a particular element have a unique set of chemical properties which distinguishes them from atoms of all other elements. Remember the difference between identical and unique, right? There's definitely a difference there. And it's why we use unique here than instead of identical in John Dalton's theory. So, see, in the course of an ordinary chemical reactions, atoms can or can't appear, disappear, or change? Can. Why do we think that? Because of the law of conservation of mass? Yeah, that's a good enough explanation for that, right? Because they cannot appear, disappear, or change into atoms. I think Sam said that, right? So good job. And a particular compound, the atoms combine in a, what? Just said it 5 seconds ago.
Definite
Fixed ratio.
Fixed ratio, yeah. Fixed ratio, definite ratio, whole number ratio. Pretty much all the same thing what we're talking about here. So again, here's some examples. Water, carbon dioxide, sugar, glucose. Are there any half atoms happening here?
No.
No, right? You can't have a half atom. And then E, blank are formed when two or more elements chemically combine with one another. Any ideas on this one?
Compound.
Compound's a good one. We can also use molecule as an example. Like again, H2O is you kind of refer to it as like a water molecule, right? Have you ever heard that around? But yeah. All right. So these are when we kind of get into the articles we talked about that y'all were assigned here. So let's talk about the two main parts of the atom. First off, the electron. So discovered by J.J. Thomson in 1897 using cathode ray tubes. It has what charge? Negative charge. Awesome. Is located outside the nucleus and energy levels. The more energy the electron has, the blanket is from the nucleus. Do we think it's closer to the nucleus or further away?
Further away.
Farther away, right? Why do we think that?
Because
It has more energy and it's like, it has more energy so it travels faster so it can't be.
Kind of. I mean, there's more electrons, so the electron cloud's going to end up getting bigger and bigger and bigger because you can't just have them all right next to the nucleus, right? And that kind of defines our atom, right? So I don't think y'all were here for Tuesday, but kind of the explanation for that, if you want to think about it. So if the atom center, the nucleus, was and this kind of is spoilers for this next part, right? So let's say the atom nucleus is a tennis ball. Then the rest of the atom, the electron cloud, is the size of a football field. So if you have a tennis ball in the middle of a football field, that's essentially what you're looking at. So essentially you have a really, really dense center here in the middle, and then just a whole bunch of space for electrons, depending on how big the electron cloud is. Alright, so, speaking of which, has the mass of 1,837th that of a proton, therefore it is significant or insignificant in the overall mass of the atom? Insignificant, right? Like, if I pull out a hair in my head, it weighs something, right? But do I lose any amount of significant weight? No, not really. I use an example too, where it's just like, when I eat 1,837th of a cookie, would y'all? Maybe? No, probably not, right? You might, just because it say it's a cookie crumb, right? But it's not going to be very satisfying, right? So again, it's not very significant in the overall mass of the atom here. And then they kind of briefly mentioned with Michelins. Robert A. Michelin discovered the actual electron charge in the element using his oil drop experiment. If y'all did the article, do y'all remember what that exact charge was? Never mind. So, if you have your article notes, it's something like, you should see this number, it'd be a little familiar. It's like negative 1.5-ish times 10 to the negative 19 coulombs, which is what we use for like electricity. So you don't need to necessarily know that, but that's why there's a coulomb there, just in case you were confused. But yeah, so the important thing about this is, again, if we had 2 electrons, what would be the total charge of 2 electrons?
2 times -3 times 10 to the 19.
Yeah, Jackson, so you're about right in saying that, but the most important part is kind of what Creed filled in, where it's like 2 times this, right? So what he discovered is that basically all electrons have a multiple charge of this, right? Where 2 is 3.0, 3 would be like 4.5-ish, stuff like that, right? So that's kind of the most important part that about Michelin's experiment. All right, so again, go to the nucleus here.
Do you want to show them the cathode ray tube?
I do want to show them the cathode ray tube. So,
I have the video too. If you want to show them that video.
yeah, sure, we can go to the
That's
video.
up to you.
Do we have time for the video? We probably have time for the video. Let's do the video. So we actually have a video of the cathode ray tube, just so y'all can see that experiment in action. Because of course, just reading about it is a little boring, so seeing it can be kind of exciting. So we'll go there.
Go ahead.
Yeah.
This is a cathode ray tube. What essentially is, in
decided to apply a magnetic field to this cathode ray, and he found something interesting. We applied one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part, when you see what's happening to that beam. Those appear as though it's happening to it. It's moving, it's being repelled, isn't it, by the magnet?
So what side do you think what side of the magnet do you think is happening here? Is that the negative side or the positive side that he's putting towards that?
Negative.
Positive side, right? Because it's attracting, right?
Oh, yeah, I think.
Now,
Yeah.
here.
Now it is. Beforehand, when it was going away, what do you think that side of the magnet he was using?
Negative.
Negative, exactly.
Attracted there. We rotate some of the kids up like this so we don't see it. See what's being attracted there? And then the other pole, we see what's being pushed down. What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it
Pretty
away.
much calling it over there. But yeah.
So what does that tell you about the charge?
So yeah, it's important to do, right? Because, like he mentioned in the video, Thompson really had no idea what this was, and so he was kind of doing these experiments to figure it out. So when he did the cathode ray tube, and he put that magnet, he noticed that it had that negative charge. So here's a cathode ray tube that we have. So I'm gonna go ahead and turn it on. So again, right now, the negative side is right here. No, it's on reverse. So right now, the positive side is on here. So you see it's not moving. Now, if we know from what he said, it moves from the cathode to the anode, this negative charge, right? So if I turn it to the normal side, again, this is negative, positive. You see that it starts moving, right? So what's important about this is normal light wouldn't just like, or like, if it was just like light in there and like nothing else, this wouldn't be moving, right? Because it's just a pinwheel. But we kind of discovered through this method is that we know that there's something hitting this pinwheel in order to get it to move, right? Because otherwise it wouldn't move. So that's kind of how we discovered that that the electron is actually like a photon. It's actually an actual particle that's happening and that's going through this cathode ray tube. All right? That makes sense, everybody? Do y'all like the pinwheel? Yeah? Okay,
So-
cool.
So when are you able to see the beam? Like, in his experiment, you were able to see the beam.
And his experiment, you'll be able to see the beam. It just depends on how you set it up. For this one, you don't see the beam because there's not like a strong ray to it. I think this one's mainly just like invisible.
Go ahead and turn it on again.
Oh yeah, that's right. Yeah, true. It does show a little bit. You can kind of see it here.
So they have the tips coated with the
Yeah.
fluorescent. So fluorescent thing is something that glows when it hits with electricity. Okay, so you can see the tip glowing here. They have the same thing on that, inside the cathode ray, that piece of metal had that white coating on it.
Yeah.
And so that's what made it glow. When the electrons hit that, is what made it glow.
And you can kind of see it too, right here when I switch it. You'll see like a little flash. It kind of turns on and you can kind of see that it's going to be switching directions here. So it's a little hard to see, especially when it's not lit up, but in the darkness is a little easier to see. Alright, so that being said, we'll go back to our notes here and talk about the nucleus. And we'll get into some fun stuff. Alright, so what does the nucleus contain? What is inside the nucleus? We talked about electrons already, so what do we think it contains?
Protons and neutrons.
Protons and neutrons, right? Along with hundreds of other subatomic particles called nucleons. We don't talk about those too much. It's just important to know that there's some subatomic particles in there. So nucleus was first discovered by Ernest Rutherford with the Gold 4 experiment, which gave 3 conclusions about the nucleus of atoms. All atoms contain a what nucleus? Do we think that the nucleus is positively charged or negatively charged? Positively charged. Why is it positively charged, Ella?
Because it has the protons in it.
It has the protons in it. Protons have a positive charge, so the whole nucleus is going to be positively charged. The nucleus is very tiny, yet contains relatively what of the atom, therefore it is very dense.
Most of the mass.
Most of the mass, right? We kind of talked about it again with that that football example with the football stadium with the tennis ball, right? Like the nucleus is just kind of there, that's the rest of the mass, but the open space where the electrons are is the size of that football field compared to that tennis ball. Yesterday when we introduced this, Mr. Hobbs mentioned if you had a centimeter by centimeter by centimeter cube that had the density of an atom, how much do we think it would weigh? Give me some guesses.
It's full of just nuclei.
Just nuclei.
Okay, so
Just give me some guesses on how big you think it would be.
100 pounds.
Bigger.
Really? Wait,
Yeah.
how big is it?
1,000 pounds.
Centimeter cube by centimeter cube, or centimeter by centimeter by centimeter cube. So about like,
Over.
then there's 2.5 centimeters in an inch.
yeah. Over 100 pounds is technically correct. I heard that, but let's get some more numbers. What do you think?
10,000.
10,000 higher.
Wait.
Million.
A million higher.
Wait,
1 billion.
1 billion, I think it's a little higher than a billion.
Just right there.
Just about at a billion. Just about at a billion, right? So
It's so dense.
it is, it's super dense.
Yeah.
I think the
So-
exact
so-
number is what again?
50 million metric tons.
Yes, 50 million metric tons.
And a metric ton is 2,200 pounds, so 50 million times 2,200.
It hits about a billion.
It's a lot.
Yeah. The whole,
So-
it's super dense.
So what does that mean about how many nuclei you would need to fill that box? How much material do you have to get? Kind of like 50 million metric tons.
Yeah.
So it takes that much to get enough nuclei to fill a box this big.
Yep. So, again, like I said, the rest is mainly empty space for the atom, right? So, interesting note is that technically, and this happens in science all the time, Rutherford didn't actually discover it initially. It was kind of some of his students under him, his researchers. He wanted to set up the experiment because initially, do y'all remember what he thought the nucleus looked like initially?
The plum pudding.
Yeah, this is the plum pudding molecule. We had just like a bunch of empty space and like the neutrons or the electrons and the protons kind of floating around here. So he thought that basically when he passed those alpha particles through the experiment, they were just all going to go through, right? And so he was just like, it'll be fine. And he was just kind of discovering about radiation. So he let his students kind of do the experiment and do the observations. But then they noticed that some of the alpha particles that was getting shot started bouncing back towards them. It's like if you had a artillery shell of a battleship fired at a piece of napkin paper and it flew back at you. It's really weird. It's something that shouldn't have happened with that design of the model. So he ended up making a new design of the atom based on that experiment. All right. What you should recognize, like, do you all remember what it looked like? It was kind of like, what it had, like, what in the middle?
I think it just had one thing.
Yeah, it just had like one thing. It would be like the, proton, nucleus, what do you think?
But like just a single proton.
Yeah, he thought it was just a positive charge in there, and then that's it, and then the rest was like kind of surrounded by electrons. All right. So, what was discovered by James Chadwick in 1932? The neutron, right? So the neutron has no charge, has approximately the same mass as a what? Proton, right? So, can be thought of as a proton and an electron combined, and this is essentially number 4 is how he did it. Was he bombarded beryllium atoms with alpha particles in the nucleus, blew apart the yield stream of neutral particles called neutrons, and that's kind of how he ended up figuring that out. So yeah, that's the notes up to atomic number. So we're gonna do something real quick here. So we have all the information we need to make and draw out an atomic model of your element. We have all the information now. We know that a nucleus contains what? Protons, neutrons, and then the rest of the space is filled with what?
Electrons.
Electrons, but it's mostly what? Empty space. Yeah, exactly, right? So we're gonna do some drawing. We're gonna try to draw out the elements that we have. So if you can see, let's see, who wants to give a crack at drawing the atomic model of their element? Who thinks they can come up with something?
I mean, if I look it up. Yeah.
Yeah.
Did you look it up? Well, let's construct it based on this. So remember Rutherford's model. It was mostly right? He just had this and then a bunch of electrons around it, correct? So, but he was missing something, right? What was he missing?
Neutrons.
Neutrons, right? So, if your element contained proton and neutrons, all you gotta really do is just kind of fill in the nucleus and make sure that it's correct from your element in particular, right? So, do we know how to read a periodic table? Somewhat?
Yes.
So do you know how many protons are in an element just from looking?
It's the atomic number.
This is atomic number, right? So that we're going to get into atomic number. So you know how many protons there are, and do you know how many nucleons that you should add in response?
You look at
What
the
is
mass.
the atomic mass from?
And you subtract it.
The mass.
Atomic mass, true. I guess this one has the atomic mass on it. But you can use also the mass number, which we'll talk about in a bit too. But let's try and, for now, we'll say that, and some of the elements might be different depending on what stable form it comes in, but we'll say that the number of neutrons will be the number of protons in the nucleus for now. We'll kind of flesh it out later with depending on, again, with atomic mass, right? But just so we can start drawing this, and just give an idea of how to draw this, we'll say that. So, with that in mind, you might want to give a crack at just coming up with a rough draft. Like this is not fully formed. This is like a rough draft. Sam, you want to give it a try? Yeah. Mhm. So here you go. You had, what did you have?
Fluorine.
Yeah, fluorine. So yeah, fluorine it is a pretty small one, so it might be a little easier to try to do for fluorine. All right.
And like, there's 10 neutrons, what do I draw that as?
So how do you think you could represent that as like, should they be like separate particles, or do you think they should be all in like the same nucleus?
Well, I'm saying like to draw it as, I think like a circle or something.
Yeah, you can do like a circle, yeah, that works.
And then,
This is supposed to be electrons, right?
yeah, especially like.
Yeah.
One, so like the first one is 2, and like next one's 6, and then like that last ring.
Yeah,
is
and so
1.
that goes with Vesper, and we're not necessarily super concerned with our electron shells right now, but that's good that you know that. We're just kind of just concerned with like how many electrons on the outside.
I'll say 9.
So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You have 9 protons, and then you have 9 neutrons in there.
10.
You have 10 neutrons in there. Yeah, I think that's correct for fluorine, yeah. I think, yeah. Does that make sense for everybody? Does anybody agree with this, disagree with this model? No? Have a good idea what we're thinking about? So this is kind of a good way to kind of express it. Another way that you can express it is just like separating the protons and neutrons. So like if you drew the model out, let's say like their nucleus is super dense, but it's still made up of these different particles, right? So let's say you drew like, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Obviously this is not a circle, but you can essentially write these out and then just make sure that like your protons are labeled like this, and then your neutrons are just labeled as like empty or as non-charged atoms here, and then of course you have your electrons on the outside. So that's another way you can kind of represent nucleus. That's probably easier if you have a smaller element like carbon or fluorine. Probably a lot harder if you got a bigger element like plutonium or one of the bigger like radioactive elements. Probably way harder to represent it like that. But again, as long as we know how many protons or neutrons are in your model, that's the important part, as well as the electrons on the outside. Okay? So, it seems like y'all kind of already understand what the atomic number is versus the mass number and such like that. But we're going to do a little activity just to kind of see if we've really got this down. So, I'm going to draw out, let's say, carbon here. So, this is carbon. This number right here is known as the atomic number. This number right here is known as the mass number. Now the periodic table, it shows the number down here. It's like 12.01 AMU. This we call the atomic mass. So we're going to get into atomic mass tomorrow, as well as how to calculate it. But for now, I want you to just quickly talk with the person next to you and discuss what do we think these numbers represent for this atom. Just a quick 2-minute discussion, see if y'all are all on the same page, see if we know what these make sense to be. So if we were saying the atomic number, what do we think this part represents? If we're saying mass number, what do we think this number represents for this element in particular? All right, make sense? All right, go.
Please comment all of
Yeah. I think most of y'all probably get it first, but I think just double check. Oh,
It's not like
you got a collective going?
actually.
Yeah, you got a collective.
What do you think they are?
Protons and electrons, it's still there.
Think for the mass number?
Yeah, so,
That's like the proton, like all
Is there a mass number on that?
Huh?
Is there a mass number on that?
The mass number on this one? No. That periodic table just shows the atomic number. It's weird in the top left, but generally if you write elements out and you're trying to capture mass number and atomic number, you're going to write it like that.
Maybe it was two C's.
Yeah. So you'll see it two different ways.
Are we on the test though?
Yeah.
What do y'all think?
What do you think of atomic mass? Atomic mass is
And I already got to say.
I think the mass number is just
But it just really depends on so think about what subatomic particles actually contribute.
We're gonna do
Yeah.
that.
Yeah. So they're not counted in the weight of the atoms. So that might be some good thoughts for
That's what I
protons.
call Carolyn every night about chemistry is kind of concerning. But
Okay. So I think most of us have kind of finished the discussions up. Like I said, I think most of y'all had a good understanding of this. So, atomic number, what do you think this represents? Who wants to tell me?
number of protons.
Number of protons. Does everybody agree with that?
Yes.
Yeah, so just the number of protons here. What about mass number? What do you think this represents?
The total number of protons or neutrons.
Total number of protons and neutrons. I heard something about mass. Any other thoughts on this one? No? Do we all kind of agree on this? Okay, yeah, exactly. So this is the number of protons and neutrons. Okay, so let's talk about a little bit of a hypothetical situation here. So let's say I add 2 to this mass number. And now I've got this situation going on here. So first off, what did I add when I added 2 to the mass number here in this situation?
electrons.
two neutrons.
So I hear electrons and I hear neutrons. What do we think? So
Neutrons.
neutron camp. Why is it neutrons?
Because you already have 6 is the proton, so
Okay.
then since it's the mass number is proton and neutron, then you add it.
So what you're saying is that this number right here represents our protons, right? So if this increased by 2 and this is representative of protons and neutrons, then we had to add 2 neutrons, right? Is that what you're trying to say?
Yes.
All right. Does that make sense? Electron camp, do you have an argument, a counter argument, or we retract our statement? No? All right. So yeah, that's exactly right here. So again, we're adding 2 neutrons here, and we've got a different element. Now is carbon still carbon in this? Yeah, right? Why is carbon still carbon? What makes carbon carbon?
6 protons and 8 neutrons.
So this one is 6 protons and 8 neutrons. What about here?
6 protons and 6 neutrons.
So what's the same between these two carbon?
6 protons.
6 protons, right? So that's important to know. So let's say if we increase this atomic number by 1, what do we think carbon is going to stay the same, or do you think it's going to be different?
Different.
Different. What do we think it's going to be? Take a look at the periodic table. I heard a nitrogen, right? Yeah, exactly. So if we added 1, we have nitrogen now. So that's important to know. If you increase the protons, we change the element. Protons are very indicative of what the element is. All right? Now, we need a term for neutrons. I mentioned this at the end of the Tuesday, kind of in the middle of Tuesday, but we have a term for this. It's called isotope. So basically an isotope, if I were to define it, is essentially the same element with different neutrons, or different numbers of neutrons. So we have carbon 12 and we have carbon 14. And that's how we would write these isotopes. So we have a carbon 12 here and a carbon 14. That's no. There we go. So I'd say that carbon 14 is an isotope of carbon. And carbon 12 is also an isotope. Again, it's just, you're talking about differences in neutrons for isotopes. All right? Does that make sense? Okay, so now I have a nice little practice problem for you. That'll be, we can quickly go through here. So I'm going to display it on the projector. And we'll go through this. And so part of the, this will help you with filling in the notes, because one of the first tables you'll see past atomic number is a table that we're going to be doing that's pretty similar to what I'm about to show you. So let me go ahead and, oop. All right. So, where's my table? It's what's here? There it is. All right. So we have this table. Basically, number 223. We're gonna go that. You go ahead and write that down. You want to go ahead and make this table for your own. And we're gonna go through each part of this. Okay. So we're gonna start with this chromium right here. So we see for the symbol it's not fully complete, right? But we have chromium and we have what on the top here? Is this the mass number or atomic number?
Mass number.
Mass number, right? So we can fill this part in the bottom, right? The mass number. What do we know that is? 52, exactly. So we can fill in that part of the chart here. We got chromium, 52. Oh yeah, you know what? That's way easier. That makes so much sense. Yeah, so let's fill it in. Number 52. All right. So let's talk about the next part of this. So for the mass number, we have 52. How many protons does chromium have? Let's look at periodic table for this one. What do we think? Well, how many protons do you think chromium is going to have? Look for CR.
Right in the middle.
Right in the middle area.
26.
26? Anybody else?
24.
24. Yeah, so this is an important distinction. I said this earlier, but I want to reiterate. So just because the mass number is going to be protons and neutrons, but it doesn't necessarily mean they're going to be equal. I said that earlier just for the sake of argument for the atomic model here. But just because there's 52 doesn't mean exactly 26. It's really important to look at that atomic number and compare it to the mass number to get your answer there. So we know that it's going to be 24. So we know that that's going to be the atomic number. We know that's the number of protons, right? So with that in mind, how many neutrons do you think you got? 28, right? And how'd you come to 28, Grade?
52 minus 24.
52 minus 24. Everybody agree on that one? Yeah, exactly. So how about the number of electrons in this one? What do we think? 24, Jackson, you said how many? 24? Why do you think it's 24?
Well, if it's neutral and not bonded to nothing, then it's gonna have the same number of protons.
So if it's neutral, it's not bonded to anything, it's gonna have the same number of electrons as the protons. Is that what you're trying to say? Everybody agree with that statement? Any other dissenters? Have a different idea? No? Okay, yeah, that's exactly right. So, good. 24 electrons here. So, let's see. We're going to do one more example of this one. So, let's take this one for example. We know that we've got 25 protons and neutrons. So, first off, what do we think the mass number is on this one? 55, 55, and we got that because why?
You add the neutrons and
Add neutrons and protons, right? So 55.
And I'm impressed you guys did that without a calculator.
Yeah, y'all did that without
Mental math lives.
True. Mental math is useful. All right. So again, electrons. How many electrons do you think we got? Jackson already said this. Anybody else have a crack at this?
25. No,
20
25.
25. So 25, 25. That makes sense for everybody? Yeah, I got so 25 here. So if we look at the periodic table, what do we think matches this description down here? Manganese, yeah. So Mn. So then our atomic number is going to be what? 25. I heard a little bit. I heard 25. I heard some wells. I heard some. What do we think? 25 for sure? We're thinking 25? Okay, 25 right here. And we already have our mass number, 55. We put that right on top here. Okay? So that's kind of the process you gotta use when you're doing these tables, right? You gotta kind of pick apart and see what you're given and kind of construct the rest of the table from there in the easiest way possible, generally. Like again, with these tables, when we're not dealing with it, you can kind of assume if it's uncharged, right? Protons 25, electrons 25. So if you're giving electrons, you can kind of do that vice versa. And that's kind of the strategy we want to use using these tables, okay? What time is it? Do we have time for them to do the table?
Yeah.
Around?
Yeah, you do.
A little bit. Maybe we'll do the full table after I go over ions. I think they'll be able to have time to do that on their own.
Okay.
So, yeah. So, this should give you the ammunition to fill in that first table. That first table that you see under the mass number in your notes. I think it's, let me just pull it up so y'all can see it. It's this table right here. Should give you the ammunition to fill in this table right here. It's right under mass number here, right? So now we're going to talk about, so we've messed with protons. We changed the proton, and we know that creates a different element. We changed the neutrons. We know that creates a isotope of the same element, right? So what if we change the electrons? Let's say I take away one electron. So goodbye, one electron. What happens to the carbon here? What do we think?
It bonds to something.
What was that?
It bonds to something.
It bonds to something? Not necessarily. Not necessarily. What do we? Any other? What just happens to just this carbon? What happens to the carbon when we lose an electron?
It's positively charged.
It's positively charged. Okay, so that's a good thought process there. Why is it positively charged?
Because there's more positive. There's more protons than electrons.
So there's more protons than electrons. Do we agree with that? What do we think? Yeah, that's exactly right. So when we still have this, I mean, mass number stays the same, right? Because electrons don't contribute anything to the mass, really. We haven't changed our protons because an electron left. But what has happened is now we've got, this one had 6 protons and 6 electrons, right? I'm just going to do E minus because that's an easy way to write these, right? But now we've only got 5 electrons, so overall we've got 6 positive charges, 5 negative charges, so you end up having a plus charge on this carbon, right? So, thank you, Jackson, for that. So, we are going to call these ions. Ions is the name for any element that's positively or negatively charged. Most elements, again, like kind of what we were discussing, are neutral. But again, if you have this discrepancy between electrons, you're either going to have a negatively charged or positively charged ion, right? So, The positive charge ions, we're gonna call cations. Negatively charged ions, we're gonna call anions. Alright? So, I ended thinking, yeah, so there's this chart right here that that you can kind of see that. You have positive ion, cations, negative ions, anions, and there's a bunch of different examples. If you look over here where my marker is pointing. So there's a bunch of different examples of positive ions and negative ions, otherwise known as cations and anions. Now it's a little confusing because this is the cathode ray tube, right? But we were talking about like negative charges in the cathode ray tube, but we're calling this a cation, right? And so the main reason that is with a cathode, if the cathode is negative, what's gathering at the cathode? What kind of particles do you think would gather at a negatively charged? Protons, right? Or positive ions, maybe? These cations? And so the main reason for that is because, I mean, like we discussed, J.J. Thomson had no idea what he was looking at, so he just called it the cathode ray tube, when it's really kind of like with negative particles in the inside. So that's kind of how we redefine it, where you have a cathode representing a negative node, whereas an anode represented a positive node. So I know that's a little confusing. We don't really get into cathode or anode right now, but just to get that misconception out of y'all's mind again. So that's kind of the main reason why it's called a cathode, because again, you have cations gathering at a cathode. And then if you have anode, you're going to have what gathering at the anode? Anions, right, exactly. So, with that ammunition, we're going to fill out the second table in your notes here. And I'm going to have y'all go through this, and we're going to do this for the rest of class. At some point, for online, if you can, once you by the end of tonight, I think I set it for all the class due Sunday. Just submit the cam scan in both these tables, just because I want to see where y'all are at with these, and so that way on Monday, if we have any misconceptions about this material, we can kind of quickly cover them. So for the weekend, make sure, besides just doing a little bit of research, trying to figure out your article or your for your element, cam scan these two tables in completed, and that way on Monday we can kind of go over it and see.
Where do we cam scan them to? Like, what do we try?
There's an assignment online. It says it's the atomic structure video video guide / element table assignment. So y'all, we did what was in the video assignment. That's mainly for the online. So for this class particularly, you just have to turn in the cam scan tables for that one. But the people that are online, you got to turn in the video worksheet as well. So don't worry about the video worksheet if you are in class today. And I'm going to make sure I'll go back and edit that assignment to make sure that says that, so you don't get confused and submit what you've already done, essentially. But yeah. All right, that makes sense? Okay, so go ahead and work on this table. We've got about like 10 minutes left. Should be able to finish it. And if you don't, that's fine too. And then I'll go around and see where you're at if you all have any questions. Again, ask me, ask your classmates, talk with each other, figure out what's going on, and just go through this table right here that's in your notes, okay? All right? Yeah. I was just looking.
Yeah.
That first table's not too bad, especially since we went over that instruction.
Can we take a picture and upload it right now?
Yeah, if you're done with both the tables, I mean, go for it. Oh, you got through that. Oh.
That was the first one.
That's the first one, yeah. Second one, feel pretty confident on this one, right? Yeah. That's about right, yeah. You should probably make that camera.
Yeah, that's what.
Yeah, it seems like y'all got the point of this pretty well, so that's awesome.
Oh, wait, we
Can
did
you
this one
zoom
too.
in on the numbers?
Yeah, of course. Oh, did you not have that? Yeah, it's in your notes. So if you are, yeah, the table's in your notes for, yeah. So I can zoom in here, that's what I was talking about, so both of the tables are in your notes, and those are the ones I want you to scan.
So submit both of them.
Yeah. Submit both of them. Again, y'all don't have to do the other assignment, the video worksheet, you just wanna see those tables from y'all. And again, I'll update the, assignment for that.
Is that
but-
table we did like as practice?
The first table? Yeah, so the first table was just kinda to get you in the practice of like seeing tables like that and being able to fill out the information in there. And then the two tables that are in the notes are, one is without ions, the other one is with ions, so it's just kinda, I just wanna see the understanding from both.
I don't know. Which one do we upload this under?
It's the element, worksheet / atomic, structure video guide, I think that's the full.
It says atomic structure vocab / element.
Yeah, atomic structure vocab / element guide, thank you, I put a lot of words in that because there's 2 assignments in there, but.
I don't have the paper copy notes, I've just been doing online, so can I just?
Yeah, if you can make your own table, you can do that, otherwise, if you wanna just go home and put it into your notes that way, that works too, just really, as long as I see the table.
So like, this is oxygen,
Uh-huh.
so there's 16, like that's the mass.
That's the mass number, right?
So that would be
So what's the atomic number?
8 of each, right?
Yeah.
And
Yeah.
that would just be an extra neutron.
Yeah, right, and what is that? That's a, it is an extra neutron in that option, what is it? What is it called?
So that
Yeah.
would-
See, sometimes, like, sometimes the protons and neutrons are the same number, sometimes they aren't. And we'll talk about why some are and some aren't tomorrow, when we talk about atomic mass. Which y'all won't be
Do we
here,
fill
but you'll
these
see
in,
the
or
video
do we
on
just
that.
do the tables?
If you have time, fill in the notes, yeah, because that'll help you when we go over the study guide, because you already have everything, information in your notes. But yeah, right now, just bare minimum, just to get those tables done. And then if you have extra time, fill in those notes, because again, you should have the information to fill those notes, quick with the knowledge to fill in those notes. Okay. Since the good of you looks like you're already done, y'all have any questions on the project for me? Any questions in general about the project?
When's it
I have
due?
a question about this.
It's due Tuesday, but yeah.
Wait, so when you like the ions, it says minus 30, are you like matching the proton?
So minus 3, so what has a negative charge? So electrons do, right? So if you have a negative ion, that's negative 3. Where do we think we had electrons
just hang on a proton pair.
What? What is with the question?
You had a
Yeah,
proton,
I think
you did negative 3?
unless it's
No,
like.
like, there's more ions, so you took away the electrons.
So that's just positive, right? Because then it's like, if we've got 8 positive charges and 5 negative charges, then we have plus 3
Wait, so
positive,
this
right?
doesn't mean that you're taking it away, it's
So
like
yeah, negative, it's negative, let's say, so oxygen, how many protons in oxygen?
Yay. Wait, normally?
Yeah, normally,
8?
yeah, always has 8, right, so, remember when we kind of discussed earlier, when you change the proton, you change the neutron, the isotope. So, there's 8, right? So if you have negative 3, that means we're 3 negative charges above 1.2, right? So we're saying you have 8 negative, or 8 positive charges, and how many negative charges?